Okay, we continue. Did you hear me? Hello? Somebody on the other side? Acá me dice alguien que no me puede escuchar. Now, do you hear me? Hello? Hello, do you hear me? Sí. Es que uso este, no uso el mío. Now it's working. Now, do you hear me? Good. Okay, then we continue. So let me repeat this part because I don't know when we had the problem. So I was discussing this theorem. We are not going to prove it, but just to discuss how it is. So let me start again with this. Because this theorem is very important. It's not that we are going to use it, but it's important to understand the issues, what the objects we are using. So it says, okay, I have a norm space W, and then there says, okay, there exists another space B with a norm also, and a map phi from W to B, and this is Banach. So the difference between this and this is that this might not be complete, but this is complete. So every Cauchy sequence here converges to some element of B. So there is a map such that it preserves the norm. So phi of W in B, so this is the value in B, is equal to W in W, and phi of W, when I send all the W which is contained in B is tens. Meaning that if I take the closure, is equal to B. So, and think about this as the following. Suppose you have the rationals. Say W is the rational with the norm being the absolute value. And we know that this is not complete because it doesn't have the square root of 2, for instance, and we know that there is a sequence xn such that the square root of 2 we say is equal to this limit. And so we think of that as a number that we can compute, and this is this limit, okay? I don't know, even the Babylonians have an algorithm to compute it, so there was a Cauchy sequence at that point. And so how do we construct the B, right? And the way we do is, okay, let's consider the space of all Cauchy sequences. In W. So that's a huge space, all Cauchy sequences, much bigger than W. And now we say, but the square root of 2, you can think of, okay, there is some sequence which has this limit, but there might be another one. Which also give you the same number. Or suppose you have pi, you know that you can approach pi by, if you have a circle, by some polygon outside, or you can approach it by a polygon from the inside. And these are two different sequences. So, but you say, okay, the length of the circle is attained either by getting this with more sides or this other with more sides. So these are two different sequences that give me the same number pi. Right? So we want these two things to be the same, to be equivalent. So we say, okay, some sequence xn is equivalent to some other sequence. These are Cauchy sequence if Twiddle, say, the norm of xn minus xn Twiddle go to 0 as n go to infinity. So these are, we don't want to say that the limit is the same because that limit does not exist in W. But we want to say that they approach each other. To a whole maybe, but they are approaching. So we say these two sequences are equivalent if they approach each other, right? So then we factor the Cauchy sequence by these equivalent relations. And this is the space B. So it's a space of Cauchy sequence under the equivalent relations that every two sequences is the same if they approach each other. So this is the space B. And what's the map? Well, the map is just take some element W of W and you create a sequence W, 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 all everywhere W and take the equivalent class. And take its equivalent class. Right? So this is an element of B. And what's the norm? The norm of B was the norm of some element B of B. So remember, these are equivalent classes. So the norm of that is the limit. You take some of this Cauchy sequence and put here the limit of x n in W. So these are the real numbers. So the norm of this value is this. So this is a norm. So in particular, if W is this sequence, the norm of the corresponding value here is just that. So if B is this sequence, then the norm of B in B is just W in W. So that satisfies the theorem. So we have to, the part that we are not proving of the theorem is that this space is complete. And this you can see in the Yoshida book. It's a proof. It's not long. It's basically you have a sequence of sequences because you get Cauchy sequences of these Cauchy sequences. So you have one Cauchy sequence, the next one, the next one, the next one, and then you take the sequence that goes into the diagonal. And then you can show that this sequence converges to the diagonal one. So it's not difficult. But it's to me, it's a very deep theorem because it tells you two things. First, that the things you are dealing with when you take a complete space, it's not always something, some object which is a function or something like that. Usually there are Cauchy sequences of things under some equivalent relation. And the other thing says that, okay, if you give me some space with a norm, I can always produce a complete space. And usually what you do is you take a space with a norm and you complete. And then work with the complete spaces. And then what you do is to try to characterize some properties of this complete space. For instance, if I take the space of L2 functions, say I take f to be continuous, in some interval, say, and I take under the norm L2, and this space, this is W is all the continuous function here, I can complete it. But when I do the completion, the object, the element of B of the completed space are no longer functions. Right? And this is clear. So what we are going to see later is that there are spaces where the things start to be functions. Yes?
So I wasn't here before. Can you just tell what a complete space is?
Okay. A complete space is a space where if you have a Cauchy sequence, remember, a Cauchy sequence is a sequence in some space such with a norm such that this thing goes to 0. So that actually this is, given any epsilon, this is less than epsilon for some n, and small n bigger than this. So this is a Cauchy sequence, and it's complete if the limit when n goes to infinity of xn exists, some element of B. Yeah, so suppose you are computing something. You take a code for solving some wave equation. What this code gives you is a sequence. You put more steps and you get a solution which should be closer and closer to the solution you want. And you are doing this, and every step is in some space. But you don't know whether a solution exists at the end. So if this thing has a limit, and it might be that doesn't have a limit, because I can start doing things and at the end I get something that doesn't even satisfy the equation. Typically, for instance, you can say, okay, I have this thing and I start with something which is continuous or differentiable and go to the limit that I get something that is not differentiable, so the equation doesn't make sense maybe.
So it's like in quantum mechanics, for example, when we write a solution of the problem as an infinite sum of sines and cosines, these functions are not in L2 space because they have no norm.
Yeah.
But then you still are able to use them to find the solution. It's like that.
Yeah, this is a problem with the basis. We will not touch this, but if you look in the notes that there is there, you don't have to think of as basis. You have to think as Fourier transforms, and this is a map, which is okay. It's from L2 to L2. This map you can write with eigenvectors, but they are not in L2, so they are bad. But the map is okay. The step you do in the middle is not good, but the map is okay. Maps L2 into L2, so there is no problem. But you have this thing into the middle. So this is more the case in quantum mechanics. You say, okay, the elements of L2 are functions, right? And you think of the square of the absolute value integrated is a norm. But this space is not complete. The space that is complete is where the functions, their elements are not functions but are equivalent class of functions. Where two functions are equivalent if they are the difference of the integral, the integral of the difference is 0. So they can have values almost everywhere the same, but they can have finite number of values where they are different. So they are not even continuous. They are not functions, because if you want to say what is the value of this field here, I cannot say it, because it's an equivalent class. So I don't know the value of phi of x. When you do quantum mechanics, you cannot say what the value of phi of x is.
But you can't restrict your analysis to continuous functions, and then it would be like well-defined.
If the initial data is smooth and you have some properties, then the solution will be smooth. But there are many things that are not guaranteed. I mean, the space, you say, the Hilbert space of states is all this space is the Hilbert space, which is complete. So that's why people say sometimes, okay, this is a quantum field, and we don't know the value at some point. What they are saying is that the elements of the Hilbert space are not functions, so we don't know what the function is, what the value is at one point. And that's okay. I think it's physically it's okay. We don't know really this. We know we can integrate these functions over some other smooth function and get some values. When we measure, we do that, and that's okay, but the value at some point we don't know. And so trying to insist that you get the value is not good, because so this theorem is intellectually is very important. In practice we are not going to use anything of that, but it's good to know that things are like that, because sometimes when you get into contradictions, just remember that things are not what you think intuitively. So now we are going to go into Hilbert spaces. A Hilbert space is a Banach space, so it's a complete norm space where the norm comes from a scalar product. That's the Hilbert spaces as what we know from quantum mechanics. So we know we have a scalar product which is a map from B to B to the complex, which is linear in the entry which is on the right, and antilinear in the entry which is on the left. So this C here comes out with that C complex conjugate. And so it's linear, antilinear, and then it's symmetric in this sense. If you change the value, the two position of the vectors, and take the complex conjugate, you get this the other one. And if you put the same vector here, this implies that it's real and it's positive, and it's only 0 if x is 0. And we have the Schwarz inequality that we are going to use all the time, that says that the absolute value of the scalar product of two vectors is less than the values of the vector multiplied. In the book you can find a proof, but I'm sure that you have proven that many times in your life. But this is basically what we are going to use all the time. This is different, for instance, when we have a covector and a vector, right? And we take the absolute value. This was less than the norm of W times the norm of B. This is different because this comes from the definition of the norm of this one, while here we have the scalar product, so we know another norm. So it's different. This is basically nothing to prove here. It's just a definition of W, but here you do have to prove things. Okay, examples of Hilbert spaces. If you take tuples in Cn with this scalar product, that give you a Hilbert space, complete Hilbert space in Cn. If you take the sequence whose squares, the sum of their squares is finite, then this is a Hilbert space. And the inner product is you take the two sequences and you multiply them with the first one complex conjugate and sum. And here we can prove that this L2 is a Hilbert space. What it means is, okay, we have a space of all these tuples, sequences, and we have a scalar product. What do we need to say that is a Hilbert space? That is complete. So we have to prove that it's complete. So that every Cauchy sequence here converges to a point in the Hilbert space. So let's try a proof, just to so that you get used to this. So let's this in here be a sequence of sequences, right? So I have these sequences, and on this sequence I have sequences. And we assume that this is Cauchy, namely that there exist an n-bar number such that this here, this difference between the sequence, which has, this is the value of this difference in the norm, is less than epsilon square for nm bigger than n bar. Right, so these are sequences, Cauchy sequences of sequences. And now this is basically the same way we deal with when we're looking at CAB, the continuous function, bounded continuous function. We have a sequence of functions, and then we fix x and look at the sequence, this sequence of numbers, and since the reals were complete, we conclude that this has a limit, and this limit we call fx. Here is the same, but instead of x, we use I. So we know that since this sum is finite, every one of them is sum of positive things, each one of them is less than epsilon. So now we fix I and go and run through n. And so this is a sequence of numbers, of real number or complex numbers. So it has a limit, and this limit we call x bar I. So now we have a sequence, a limiting sequence. For each I, we have a number. So now what we have to check is that this number belongs to L2, so that it has a finite norm, and that the sequence of sequences converges to this sequence. Here I have to explain this a bit. Let's see. What we want to prove this. Check that here we have a finite number, k. And we are taking the limit. So we start with this sum. To k, the xjm minus x nj square. This is finite because we are in the sequence, in the Cauchy sequence less than epsilon. And now we take the limit n going to infinity. Right? Since this sum is finite, I can put the limit inside. If I have infinite here, I cannot do that. But since the sum is finite, I can put this limit inside, and so I get this. And so this is less than epsilon square, So I get that this limit is also less than epsilon squared, right? So I have this result that for k finite, this thing is less than epsilon squared. But k is arbitrary, and this is a sequence which is bounded. So I cannot overcome this epsilon squared. So here I can substitute this by infinity. Right? And so I know that this sequence converges to this one.
Your substitutes m for infinity.
Sorry?
Your substitutes n for infinity.
You are?
Your substitutes the value of n, right?
Of n. From going to here to here.
No, after that, that infinity you put there
Is for k.
is for k.
Why? Because I know this is true for any finite k. But for every k, this is bounded by epsilon squared. So in the limit, right, this is a sequence, growing sequence, which is bounded. So I can take the limit. This converges. Right? Let me explain this. What is the difference between k and infinite here? I say that the infinite is the limit of that thing, right? So these are numbers, let's say, call it s of k, right? So I have a sequence, s of k, and I know that this sequence is smaller than epsilon squared, and it's growing, it's monotony, it's not decaying. So I have a lot of numbers here, this sequence, and it's bounded by epsilon squared. So since it's bounded by epsilon squared, and it's monotony, I know that it has a limit. So limit of sk when k goes to infinity is some number. And this is value of this when I put infinity here. Like this is really what this symbol means. So this number is finite, exists, and is less than epsilon squared. So I know that my sequence converges. My Cauchy sequence converges to these values. And now, as was in the case of functions, I have to check that this sequence also belongs to L2. Right? So I have to check that the sum of these things is finite. And how I do that? I want to compute this norm, and this I write as this element, I add and subtract the sequence with some n big enough. So if I do that, and I use the triangular inequality, I get this one and this one. Since these are Cauchy sequence, you can show that these are bounded. So this is less than some m. And this goes to 0. So this is less equal to m2 or to m, whatever you want to put. Right. So these also are bounded. So this space is complete. So this is basically the same thing we did with the functions, except that here we have to prove that the functions were continuous. Here we have to prove that they are in L2, which is actually easy. But the way of finding it is the same, so let me repeat it. You start with these sequences which are Cauchy. You get some number here, so you have you have several sequences like that. N equal to 1, N equal to 2, etc. All sequences. And then you start, we take one I and go like this, fix I, and then you come like this. And since they are approaching complete, they are also approaching each point. So this sequence for I fixed has a limit, and this limit you call xi bar. You do this for each I, and you get this sequence. This sequence here. And then you show that this sequence is the limit one, so that the norm of x I n minus xi bar, this is L2, goes to 0, so it's converging to this one. And then you show that the norm of xi bar in L2 is finite. So it's an element. This xi bar belongs to L2. That's the flow of the proof. It has some arguments which are not trivial, like I have to take this k to be finite first and do all these things. Huh? This part is not simple. It's tricky. So here we have some other examples. The space of measurable functions with square integral, which are square integral in R, and which are identified f is equivalent to g if the difference, the absolute value of the difference is 0. Here is notice I am using measurable functions. We don't introduce measurable functions. In the notes there is a chapter for measurable functions, but we are not going to use it in any case. But if you want to know what the elements are just measurable functions under these equivalent relations. For instance, this function and the function which is similar to that but with a point which is different, or some number of points with finite number of points which are different are equivalent. So if this is G and this is F. So G is identical to that, except at this point. These two functions are the same. So if you ask an element of L2 what is the value at some point, you don't know. Right? There is no way to know. But now we are going to use some other spaces, in particular Sobolev spaces, which are spaces where the norm is like this. So you can write it as f with f, this being the L2 norm, the integral, plus the derivative of f, So it's a Hilbert space. Second derivative, etc. And these are Sobolev spaces. And if you, depending on the dimension, if you take many of these, say this number big enough, the element of that are continuous function, or the elements are differentiable functions, and so on. In general, we are going to take these spaces so that the functions are differentiable, once differentiable. These are the spaces to treat partial differential equations, some of them at least. So we are going to study tomorrow some properties of Sobolev spaces. Okay? So now we are going to study some properties of Hilbert spaces, why they are good. Hilbert spaces are good because the scalar product allows you to get the perpendicular spaces, and this is important. So first, let's talk a bit about closed subspaces. So I have a Hilbert space, actually this is true for Banach spaces. I have a Banach space with some norm, and I want to describe some closed subspaces. So for instance, if you take C3, the subspace generated by these vectors, all that will be the span of 1, 0, 0 in the complex. This is a subspace, and it's closed. Closed means, from topology, that I forgot the name. The complement. The complement is open, right? So this is a closed subspace. Another one you can take is, for instance, see you have the functions H0. H0 is the same L2. It's a Sobolev space where you take just a function, the norm of the function, not the derivatives. And you take all the functions that vanish between 0 and 1. So take the functions in R with this norm, and take all the functions that vanish in this. So these are functions like that, for instance. So they are 0 except in a subset of 0 measure, right? So can be functions that have some points here which are different from 0, but in general only in a finite number of values, in a set of measure 0. Then the subspace of all these functions, right? Because if you take two functions of this sort, say this one and that one, they are 0 here. If you add the green one with the yellow one, you get another function that is 0 here, except that. So this is a vector space also, and it's closed. It's closed means that by taking limits, I cannot get something that is not zero here in an interval which is finite length. No? So this is a subspace that is closed. If you take M to be the continuous functions in some interval as a subspace of H naught, right? So these are the functions that are square integral. This is your space. This space is not closed. Huh? Why? Because you can have a Cauchy sequence inside this space that take out with this norm that takes you out from the continuous function. Huh? So it's not closed. This is interesting, sometimes appears. If you take a Hilbert space or a Banach space, take any subset of it and consider the intersection of all subspaces that contain K. All closed subspaces. Then the intersection of all these closed subspaces is also closed, and it's a subspace because it's intersection of subspace. And so that gives you a subspace that is closed. For instance, if you in this example you take K to be the continuous functions, and you look at all closed subspace that contains this space, you will get the whole space. Because basically anything here you can approximate by things here. Now, this is true for Banach spaces in general. Now, a property which is interesting happens when you have a closed subspace here in a Hilbert space, and you look at the space perpendicular. So suppose you have this is M in 3D, and the space perpendicular is this space like that. And so we are going to see what properties this subspace have. And so we are going to prove a theorem that says, let M be a closed subspace of a Hilbert space, H, then M perpendicular is also a Hilbert space. That is closed. It's a subspace that is closed. Moreover, M and M perpendicular are complementary. That is, every vector in H can be uniquely written as a sum of a vector in M and another vector in M perpendicular. So this in finite dimension is something we all use, right? We say, okay, suppose M is this one, M perpendicular is this one. So every vector here, I can write down as a vector here, unique vector here, and unique vector here. And these two are unique. I just project down here and project down here, right? So now we are going to prove it for infinite dimensions, that we have the same property, and this is not trivial, and we will see that implies very powerful things that we are going to use in the course. So let's take a break, because to prove this we need to be full conscious. Okay? So let's make a break. We continue at 12:15, sorry. I'm not conscious already. 12:15 we continue. So we want to prove this theorem. So that the theorem says, okay, if you have a closed subspace of a Hilbert space, then the perpendicular to it is also a Hilbert space, and you can write any vector as one belonging to M and one belonging to M perpendicular. So every vector can be written down as y plus z, where this belongs to M and this belongs to M perpendicular. And these two are unique. And this theorem is very important. When you first look at it and say, well, it's sort of trivial and unimportant, but it's really, really very, very important. So this theorem is what is going to allow us to prove, for instance, the solutions to the elliptic problems or hyperbolic problems exist. It's incredible that such a thing, such an abstract thing, can be so useful. So we'll see later on the corollary. So let me prove this. So we can very easily see that this is a vector subspace, because, right, if x and y is 0 for all y in M, and z with y is 0 for all y, then x plus z alpha z with y is also 0. So it's a subspace, it's closed under sum and product, and you can see that it's closed. How do you see that it's closed? Well, you take a sequence of elements xi, which are in the perpendicular, converging to some x in H. We know that it converges to some x because H is complete. And then we look at x, the absolute value of x with y, and this we can write as the absolute value of x minus xi with y. Y is in M, so this is in M. And why we can put this xi here, because the xi's are in the M perpendicular, so with y are 0. And so now we use the Schwarz inequality to say that this is less than the norm of this difference times y, and this tends to 0 because this difference goes to 0. And therefore x also belongs to M perpendicular. So we know that it's a Hilbert space, because it's a subspace that is closed under sum and scalar product, and the Cauchy surf, and is complete because Cauchy sequences in this space gives vectors as limits which are in the same space. So the only thing we have to prove is the complementarity, namely that we can write any vector as a sum of a vector in M plus a vector in M perpendicular. So for that we are going to use a minimizing principle. So we are going to find this vector set approaching this like that. We are going to make a Cauchy sequence here in M. We'll see how. So let's take a vector x here. This is going to be our vector here. We want this x, we want to write as a set plus something. I don't remember what is z plus y with this in M and y in perpendicular. So we want to find first z, and then y is the difference. And then once we know that y is the difference, we check that this is in M perpendicular. So we look at this distance. This is the infimum among all the w's in M of the difference between x and w in H. Right? So now we move here in M only, and we look at the distance, right? And here notice we use the infimum because we don't know whether we are going to reach the minimal distance. I don't put minimum here because we don't know. What we are going to see that there is a minimal.
Can you just say that this is also in M because M is a Hilbert space? So every sequence in M will converge to a point in M.
Every Cauchy sequence.
Yeah.
Yeah. What we have to show now is that this sequence is Cauchy.
But it isn't by construction.
What we are going to see. So we have this deal with this infimum, right? So we can build a sequence such that this difference goes to D. Right? So I can, since this is the infimum, I can get arbitrarily close with vectors to this value. Okay?
So this sequence is not Cauchy yet.
Not yet. So it's a sequence that we move and we are closer and closer to the infimum. And what we want to check is that we really get to the minimum, to the infimum, to that value with a set in this. So we have to check that this sequence is Cauchy. This doesn't work in general. If you take a Banach space, you could do this, but in the Banach space you will not find, in a generic Banach space, you will not find the point.
Because in Banach space there is no notion of sequence.
Yeah. But you could do this, right? There's no problem in doing this. But you will not get to the Cauchy. So it's subtle. So now we are going to check that this is Cauchy. So we take the square of the norm of two different points in the sequence, add the x in both, and rewrite this and you can see now you use that this is a scalar product, right? So this here is set n minus x minus set m minus x square scalar product with the same, and you open all these scalar products and work for a while, and you will get this term here. There are two terms which are positive with a 2, and there is a term which is negative. This one here. This is called the equality between this and this is called the parallelogram rule, law. And if you want to remember, is you have two vectors here and another vector x, and you are looking at this side, this vector and this vector, and checking the formula. of what are this distance between this distance. So it's a relation in the parallelogram. So, and this is equal to this in here, where we have just added these two terms here, divided by 2, put a 4 outside, and then get the x here. And so, this here is an average between two quantities divided by 2. So, this vector, and we have a minus sign here, so we can take here the smallest things we can think of, and this is the minimal distance, because this is a vector which is in M, and this is the x, so this has to be bigger than d squared. So I can change this by d squared and use a larger or equal, right? So I get this in here. Now, this here tends to d, the distance. This here tends to d. And so we have 4d minus 4d tends to 0. So this thing tends to 0 when n and m goes to infinity, and so it's a Cauchy sequence. Okay? What we have used here is the parallelogram law. And there is, I think I put it here, it's a problem which is in the notes that says this is a way of stating the parallelogram law, and you can check that this holds for any norm that only if and only if the norm comes from a scalar product. And in fact, you can write down the scalar product using the norms, and this is expression. So x with y is something that you write down just with the norm of the differences. The difference of the vectors, the sum of the vectors, and here with an I. So this is a very interesting expression to write down the scalar product in terms of the norms. So what we know now is this sequence approaching the infimum is Cauchy. Therefore, this converges to a unique set in M. So the only thing that we have to check now is that the difference between x and z is in M perpendicular. So we have to prove that y with d is equal to 0 for all b in M. So we take some arbitrary b in M and some arbitrary number t and look at the d square. We can write the d square as z x minus z because this attains the minimum. And this is smaller than this. Why is smaller? Because smaller or equal because this is a minimal distance. If I move on M with t times b, I will be increasing the distance, not decreasing, right? And so this is x minus z is y, so we get this relation. That this difference is equal to d squared. And now we use the scalar product, and so we can write this here like that. Right? It's just a calculation. But notice the following. Here we have the real part of y with b, and we have a quadratic term and these constants. So this is a polynomial of second degree in T. But so I think here I'm missing a. Yeah, we have the less equal here. So this should be like this. So we have d squared less than this. And for that to be true for all t, this term has to be 0. Why? Because if this is not 0, I can take t very small, so that this is very, very small. And according to the sign of t, I can make it smaller or bigger than d squared. Right? So the real part of the scalar product of y with b is 0. Now if you take I times t, you will do the same calculation, and here you will get the imaginary part. So you can, the same way you can prove that the imaginary part has to be 0. So we conclude that the y with b is equal to 0 for all b belonging to M. So y is in M perpendicular. Right, and that concludes the proof. Okay with the proofs? Questions on the other side? Okay, I will continue. A storm?
I think so.
So the first corollary is that M perpendicular is the same as M. So that taking perpendiculars, we don't get anything different. This is like when we were doing the dual of the dual in finite dimension was equals to B. This is similar. We don't get anything funny here. So we will prove this showing that M is contained in M perpendicular, and the other way around, so that they are the same. The first one is easy, right? Because the vectors here are vectors which are 0 if B belongs to M perpendicular. And in particular, all vectors that belong to M satisfy this by definition of them perpendicular. So this is easy. So the other one is more difficult because we have to show that these are included here. So we do the following. We take some x in M perpendicular and write it down as x1 plus x2, where this is in M and this is in M perpendicular. Let me think about this a bit while we are doing this way. 1 second. Okay. So far we haven't done anything. We say, okay, this is a vector which is in H, so I can write it as a part in M and a part in M perpendicular. But since M perpendicular and M perpendicular are complementary, and this is in M perpendicular, this here should be in M perpendicular perpendicular. So this should be 0. And therefore the x is also in M. So this is 0, therefore x belongs to M. So we are using here twice the uniqueness. We say, okay, we can write this in a unique way as a vector like that, and also we can write it as a unique way as a vector here and a vector here. But the vector here has to be this one, and this will have to be this one. So this has to be 0. And now, this theorem we are not going to use, so it's not actually I use it for something that we are not going to talk here in this course, so it's nice to follow the argument, but we are not going to need it. So now for the next corollary, which is a very important theorem actually, I need to discuss dual spaces. In finite dimension, we say, okay, we have a vector field B, we look at the dual space, and this was a space of 4 linear functionals acting on B, giving me numbers. Some numbers, in general, a complex number. Here in infinite dimensions, we have to qualify these things a bit. And what we say is that, okay, we want continuous linear functionals. So what it means? Continuity means that if I do this in this value, and this in this value, another vector, and take the norm in the dual, this is as absolute value because these are numbers. And we want this smaller than epsilon, then we have to take b minus b prime smaller than some delta, right? That will be continuity. But this is just sigma db minus b prime, and this is less or equal to norm of sigma times norm of b minus b prime. So this is delta, so we know that the epsilon will exist if this thing is bounded. So this is less than infinity. Here we are using infinite dimensional spaces. So what we are saying is that we are going to take only linear functionals that are bounded. Okay? That's important. Not any linear functional because they can be infinite. The norm can be infinite. but the linear functions that are bounded, which is the same as being continuous. So here the dual spaces in infinite dimension we always take to be the continuous linear function or bounded linear function. It's the same. And with that in mind, we have the following theorem. So let phi be an element in the dual. So this is a continuous linear function. Then there exists a unique y in H such that phi of x can be written as the scalar product of y with x. So in the infinite dimension, this is what we say. If we have a T which was symmetric, a 2 tensor, and positive definite, then we can have the inverse. This is a sort of a matrix, and we can compute the inverse. And so we have a map. This is scalar product. We have a map. We can write every sigma as a T of some vector with a hole here. So there is always exists a y. Given the sigma, there exists a unique y. Because injectivity, basically. Here in infinite dimension is not so easy, but we can have it because the theorem. So it says every element of H prime, I can represent it as an element of H with the scalar product. So phi is y. And so there is a naturally invertible map between H and H prime, because it says, give me phi, I can give you the y, so it goes from H prime to H. Given an element of that, I can get an element of that trivially, right, by just the scalar product. So we have an invertible map between these two things, a natural map. So let me prove this. So let's consider this space. M is the space of all x such that when I apply it to phi, I get 0. Since this map is linear, M is a subspace of H. Right? Because if 5 of x is 0 and of y is 0, since this is linear, see, if these two things are 0, these are 0, so this also is in M. And now we want to show that it's close too. Since phi is continuous, it is close. Why so? Because if we have some sequence which belongs to M, this is 0. So if this sequence converges to some value x, then phi of x is also 0 by continuity. Okay? Because phi is continuous. So now we are in the setting of the previous theorem. We have M which is close, and so we have M perpendicular and complements M. If m perpendicular is 0, then m is equal to h and phi is the 0 map, right? That could happen. So now we suppose that this m perpendicular is different from 0. And we chose omega belonging to m perpendicular. And we can adjust the value of omega such that phi of omega is equal to number 1. We take some omega and then multiply by something so that it takes this value 1. And now we take any other element b in m perpendicular and do this calculation. B minus phi b times omega. And this also belongs to m perpendicular because b is m perpendicular and omega is m perpendicular. And now we apply phi to this. When we apply phi, we have phi of b minus phi of omega, and this is 0. Why? Because phi of b, we have phi of b here minus phi of b times phi of omega. But phi of omega is 1. So I'll do this calculation here. This is phi of b minus phi of b, which is a number, times phi of omega, and this is 1, so the whole thing is 0. So this vector, b minus phi b omega, belongs to m and belongs to m perpendicular. Right? So this vector has to be the vector 0. Right? So what it says is that this vector space m perpendicular is one-dimensional because we can write any b as phi of b times omega. Right? So we are in the situation where we have a big space here and a one-dimensional space going like that. And now we want to find the y. And this is easy. The y is omega. This omega is unique over the norm of omega squared. Why? Because if we put this in the scalar product, this is the y. And apply to x, we get there. And how do we check this? So because of the previous theorem, we know that we can write any x as some alpha times omega plus y, where this belongs to m and this belongs to m perpendicular. Right? So now if we apply 5 to this gives me alpha times phi omega, which is 1, plus 5 of y. This is 1, this is 0, so this is alpha. So 5 of x gives me alpha. And if I apply to this formula, 5 of x, I will get omega over absolute value of omega squared, and here I will get alpha omega plus y. This with this give me 0, and this with this give me 1. Give me alpha. This and this divided by this give me alpha. So this is the expression and this is why. So every element of the dual can be written as an element of H and the scalar product. Still seems to be okay, what's the deal with this? But we are going to be that this is very important to see. We are using, for instance, with this we can prove that there is a solution of the Laplace equation. And we are going to use it later on the course. So this is very, very powerful theorem. And also we can prove that if we have an equation, say like this, for a system, with some initial value, then there is also a solution using the same theorem. So it's a very powerful theorem that comes from this. So I advise you to this theorem, to understand it, to prove it, because it's a good piece of stones to build your knowledge about these things. So it's good to look at it. It's very important. Very simple. We did in a very abstract in some sense, very simple, but very powerful. So it hides many things.
But it only works for bounded operators, right?
For bounded linear functions. Doesn't mean that the operator is bounded. For instance, here this Laplacian of u is not bounded. But we are going to find a solution. Because what is bounded here is this in here. We are having this in some space, and so this is going to be bounded, not this. But the scalar product here is not. Here the scalar product for this is the gradient. And you have to check that in which cases this is scalar product, etc. So we have to do this, a lot of things before reaching here. But there is a scalar product, and with this scalar product, this is bounded, and we write this as the integral of rho times b. We look at this problem. If we integrate by parts, we get this with a minus or a minus. So we'll see this, but it all boils down to this theorem. Okay, questions on the other side? Tomorrow we are going to have an hour or so for discussing how are you doing with Julia, etc., the first lab that we send you, and so that be prepared for the second lab. And also we are going to say something about the homeworks. You should be doing the homework 1 and homework 2. We have to fix the date, but probably we will ask them for the Friday next week or so. So we will go like one week the phase. Okay? No questions? Is somebody alive? Yes? Okay. So I close now.